find the relative extrema in intervals where f is increasing or decreasing, we're going to have to start by finding our critical numbers, which means we need to know where our derivative is equal to 0 or does not exist. And to find the derivative, remember that f of x is x over the square root of x squared plus 2. We'll have to use quotient rule. We'll also have some chain rule. And I'm just going to rewrite this as x divided by x squared plus 2 to the power of 1/2. So to find the derivative, we're going to have low x squared plus 2 to the 1/2. D high, well, the derivative at the top is 1, minus high x, d low, and the derivative of the denominator is going to be 1/2 x squared plus 2 to the negative 1/2 times the derivative of x squared plus 2 is 2x. All over the denominator, x squared plus 2 to the 1/2 squared. If I clean this up a little bit, I've got x squared plus 2 to the power of 1/2 minus, I could go ahead and simplify this a little bit because the 1/2 times 2 cancels, and I have x squared, x times x, which would be x squared, times x squared plus 2 to the 1/2 power, over, when I simplify this, 1/2 times 2 is just going to give me 1, so I have x squared plus 2 to the first power. I'm sorry, this should be a negative 1/2 power. Negative 1/2, pulling that down. And to get rid of that negative exponent, we're going to multiply by its conjugate, x squared plus 2 to the positive 1/2, both on top and on bottom. If I distribute this x squared plus 2 to the 1/2 power to both terms, I have x squared plus 2 to the 1/2 times x squared plus 2 to the 1/2 gives me x squared plus 2 to the 2/2, or to the first. Here, when I distribute it, those two would cancel, and I just have minus x squared. On the bottom, I have x squared plus 2 to the first times x squared plus 2 to the 1/2 is going to give me x squared plus 2 to the 3/2. And I'm going to finish simplifying this because now I have x squared minus x squared, so those cancel. So I have 2 divided by x squared plus 2 to the 3/2 power. To find the critical numbers, I need to know where is this equal to 0 and where does this not exist. Well, again, we've got a fraction. The only way that this could be equal to 0 is if the numerator is equal to 0. Well, that's not even possible. So there are no critical numbers. There's no place where the derivative would be equal to 0. But we could also have critical numbers where the denominator, x squared plus 2 to the 3/2 power, is equal to 0. Well, that would happen if x squared plus 2 equals 0. X squared then would have to be negative 2. And again, we have an issue because we would not get a real number. X squared can't be equal to a negative value if we're looking at real numbers. In other words, there's nowhere where the numerator is 0, so there are no critical numbers where the derivative is 0. There's nowhere the denominator is 0, so there are no critical numbers where the derivative doesn't exist. That means that this has no critical numbers. If we look at a number line and we want to compare the derivative of f to f, there's nowhere where the first derivative is going to change sign. So it's either positive or negative, which makes sense if we go back to our first derivative. 2 is always going to be a positive value. X squared is always going to be 0 or a positive value. So if I take 0 or a positive number and add 2, it's always going to be positive as well. So I have a positive divided by a positive, regardless of what x is. My first derivative is positive, so my function is increasing everywhere. So we can say that f is increasing for all values of x. our function will always be increasing, in other words. Now to find the inflection points and the intervals of concave up and concave down, we need to look at the second derivative. So our first derivative here, I'm going to rewrite as 2 times x squared plus 2 to the negative 3/2. That way I just have chain rule and I don't have to worry about quotient rule with it. So the second derivative would be 2 times negative 3/2 x squared plus 2 to the negative 5/2 times 2x. Well, those 2's could cancel. So I have negative 3 times 2x is negative 6x. And to make this exponent positive, we'll drop it down into the denominator. We could have changes in concavity anywhere that the second derivative is equal to 0 or doesn't exist. In order to be equal to 0, the numerator would have to be equal to 0, and that would happen if x is 0. In order to not exist, our denominator would have to be equal to 0. But again, this would mean that x squared would have to be equal to negative 2. We've already established that that can't happen. So our denominator is never equal to 0, which means we have one possible inflection point at x equals 0. To determine whether or not it is in fact an inflection point, let's look at a number line. Let's look at the sign of the second derivative to determine the concavity of the function. Our denominator, regardless of what x is going to be positive. Again, if I plug in any number, I'm either going to get 0 or a positive when I square it. If I add 2, I'm going to get a positive. So the denominator is always positive, which means the sign of the second derivative will be determined solely by the numerator. If I plug in a negative value, a number that's less than 0, then I have a negative 6 times a negative is going to give me a positive. If I plug in a value that's bigger than 0, a positive number, then I have negative 6 times a positive number is going to be negative. So when x is less than 0, my function must be concave up. When x is greater than 0, it must be concave down. So we can say there's a point of inflection, or an inflection point, at x equals 0. Because the second derivative changes from positive to negative. The graph is concave up, where x is less than 0, because the second derivative is positive or greater than 0. And it's concave down, where x is greater than 0, because that's where the second derivative is negative or less than 0. And now we're going to use all of that information to see if we can sketch a graph of the function. So we know one point on our graph. We know that the x and the y-intercept are both 0, 0 at the origin. So we'll start by plotting that intercept. We know that our graph is going to be symmetric about the origin, which means that if I know what the right side of my graph looks like, I can reflect it over the x and the y axis to get my left side, or vice versa. I do know that I have two horizontal asymptotes. I have one at positive 1, y equals positive 1. So we'll sketch that in. And I have one at negative 1. I know specifically that as x increases, I'm approaching the positive 1, and as x decreases, I'm approaching the negative 1. I also know that there are no vertical asymptotes. My function needs to be drawn so that it's increasing everywhere. So I'm going to be approaching -1 on this side, and then I'm going to be increasing and approaching +1 on this side. I know that before my inflection point here at 0, 0, my graph is concave up, and I know that after it's concave down. So this side of my graph has to be concave up, increasing, and approaching -1. This part of my graph has to be concave up, concave down, increasing, and approaching +1. And notice that this graph that we just sketched does meet the criteria of origin symmetry. If I took this part of my graph over the X and the Y axis, I would get the left part of my graph. So we have the right intercept, which is also our inflection point. We have the right concavity, concave up where X is less than 0, concave down where X is greater than 0. Our function is increasing continuously. As X approaches -infinity, as X decreases, our function approaches -1. As X approaches +infinity, as X increases, our function approaches +1. Before tomorrow's lesson, what I'd like for you guys to do is I'd like for you to attempt the problems on day 2 of curve sketching. So the next pages in your note, pages 19 and 20. They're very similar to what we've done here. So I'd like for you to try to see if you can find the asymptotes, symmetry, and intercepts on your own. And then in problem 2, I've given you some criteria, and I'd like to see if you can put all of that together to come up with a sketch of a graph that would meet all of that criteria.